All right, moving on with the next example. It says a sprinter on a high school track team can achieve an average acceleration of 3.0 meters per second squared. So for me, as I read through questions, I always like to write down the pieces of information they give you. And right here, they've given us an acceleration, 3.0 meters per second squared. From rest to a maximum velocity of 11 meters per second. So we've got VF and VI. Something to take a note here is that if you're starting from rest, that means you're not moving. So your initial velocity should always be 0 at rest. What his maximum velocity was 11. How long does it take the sprinter to reach his maximum velocity? So T is the piece of information we're missing. So if we look back to our formula, A is equal to VF minus VI divided by T. We can plug in the piece of information we have to solve for our T. For A, our piece of information is 3 meters per second squared. I'm just taking off the meters per second squared to figure out the math. Mostly just because I don't want it to confuse you with being more letters there. Our VF is 11 minus our VI, which is 0, all divided by T. So we can't just get rid of that T. We've got to, well, we can, but we got to do some cancellation and some movement here. So before I do anything here, I'm gonna just get rid of this 0 because 11 minus 0 is gonna give us 11. So I'm just going to rewrite this without the 0. And now we've only got 3 things to worry about. So we got 3, 11, and T. So our next step here is to move that T. So what we're always going to be doing is moving the T. We don't want that T on the bottom. We always want the T on the top, and we want the T on the top by itself. So being at the bottom of this 11 is not good. So it's like 11 divided by T. So we do the opposite of dividing, which is multiplying. And we multiply both sides by T. Okay? So by doing that, we end up with 3.0 T. When you multiply a letter by a number, you can just write it like this. You don't have to write times T is equal to 11. The T's are gone because it's like T, it's basically, I'm going to do a little caveat over here. It's basically saying 11.0 T divided by T when we multiply that by T. So if we had 11T divided by T, anything divided by itself, we can cancel that out. So that's how we're left over here with just 3T equals 11. I guess I don't need to rewrite that. So our next step is to get rid of the T. So this is 3 times T. We don't want the T there at all. Or sorry, we don't want the 3 there at all. So those are multiplied together. We want all the numbers on the right side and keep the T on the left. So to do that, I'm going to divide each side by 3. Because really what it means here is, before I did that, what this says right here is that 3T is equal to 11. But we don't want to know how much 3 times the time is. We want to know what just the time is. So we don't want that 3 in front. So to get rid of it, we divide by 3. And it's a balancing act always. We've got to do it to both sides. So we go 3.0t divided by 3. Gets rid of that 3. And we're left with t is equal to 11 divided by 3. So if we do that out in our calculator, we will get 3.66 repeating. And I always want it to be 2 decimal places, so if it's 6, 6, 6, a bunch of 6s, we want it to just rewrite 3, 6, 7. Okay? So our answer here would be 367. That is a time. So if we go back, this is in seconds, so it should be an S there. Okay? So 3.67 seconds. All right? So that's how we do that. Just to make sure you remember that if we're rounding, we want 2 decimal places. We always go to the 3rd decimal. If that number is greater than 5, then we need to round this number up. Okay? That's how we got 3.67. Okay? Let's try our last example. It says a group of children riding an inflatable tube start from rest and travel down a hill. 2 accelerating at an average. I need to check why this is 2. We're not sure why it says 2. Because that 2 isn't in the original question. Oh, this 2 is apparently supposed to go right here. So when I copied it, it didn't work. Perfect. Okay, so let's start over again. It says a group of children riding an inflatable tube start from rest and travel down a hill, accelerating at an average rate of 1.15 meters per second squared. Okay, so this is an acceleration question. It literally says in the question they accelerated. So we need to figure out all of the pieces of our formula. So we've got acceleration, velocity, final velocity, initial, and time. So let's look for our acceleration. In our formula or in our question, it says 1.15 meters per second squared. Also in this, it says they're traveling for 6 seconds. That is a time, so we would write 6 seconds. Our VF and our VI. So at the very first of this question, it says a group of children riding on an inflatable tube start from rest. Remember in the last question that rest means 0. So whenever you're at rest, that means you're not moving. So our initial would be 0 meters per second. All right, so that means that our VF is what we're missing. That's the piece we want to find out. It says determine the speed the tube reaches near the bottom of the hill after traveling for 6 seconds. So we want to find out what, after 6 seconds, how fast are they going? What is their velocity? So we need to write down our formula just like we did before. And then use it to solve. So I'm going to plug these pieces in. Our acceleration is 1.15 is equal to our VF, which we do not know. So I'm going to write VF minus our VI, which is 0, divided by T, which is 6. Again, if we have a 0 in there, I'm just going to get rid of it. Because anything minus 0 is 0, or is the same thing. It's not going to make any change to the question. I hate There you go. So now, just like before, we need to solve for this. We need to find out what VF is. We need to bring all the numbers to one side and all of the letters to the other. We're going to keep our letters on the right, and let's bring our numbers to the left. So just like before, to get rid of that divided by 6, we're going to multiply both sides by 6. In doing that, we get 1.15 multiplied by 6 is equal to VF. Because 6 is on the top and 6 is on the bottom here, that cancels it out. So then we're left with whatever 1.15 is multiplied by 6. So if we do that out in our calculator, we will get an answer that hopefully is right. So when I do that on my calculator, I get 6.9. That's a velocity, so that's in meters per second, okay? And because there's no extra decimals here, that's fine. You can keep it that way. Just circling our answer. So that's how you would do a question like that. These examples are coming from this slide that says acceleration examples, right? So how do we graph non-uniform motion? Well, it says the position time graph for an object that is accelerating versus an object that is slowing down. This is what it would look like. So we've got a thing that's speeding up. So you see that on the left-hand side. This would be speeding up. And this would be slowing down. On the right-hand side, you have a velocity time graph for an object that's accelerating versus an object that's slowing down. Okay, so accelerating, it's going in that positive direction. Decelerating, it's going in that negative direction. Okay. Slowing down or negative slope always equals a negative acceleration. So negative acceleration means that you're slowing down. So if you ever see something like 5 meters per second squared, that means they're speeding up. Negative 5 meters per second squared means that they are slowing down. Okay. So how do we determine the acceleration from a graph? Well, it's not too difficult. We just need to find out basically 2 dots on this graph, or actually 1 dot, and then we can find out its acceleration. Okay. So I don't know if there's an example of that. Perfect, there is. Oh, was this practice back here? It says determine the acceleration of the object by choosing 2 points on the graph and use your formula for acceleration. So we can do this one as an example. Let's choose this point and this point. So we're going to choose those 2, and we're just going to write down their velocities and times, and we can then solve for acceleration. So maybe I'm going to choose something farther away, just so that we have some space. Let's choose the first and last dot. So on our x-axis, that's this one, we've got our time. On our y-axis, we've got our velocity. So whatever we find out on the left side, that's going to go on the top of our equation. See, top. The time is going to go on the bottom of our equation. So I'm going to figure out what the velocity and time is. So the velocity The y of this one is 1, and the time is 0. I guess it's better if I write it like this. And I don't put 2. So this is our velocity, it's 1 meter per second. And over that time is 0 seconds. Okay? And then at this one, we've got our velocity at 6 meters per second divided by our time, which is 5 seconds. Okay? So that is that. So now how we would figure out our acceleration, we just got to find the difference between those. So this would be our initial and this would be our final. So we can just solve by plugging those things into this formula. I'm going to do that on the edge here. So our acceleration is equal to our velocity final, which we know is right here. That is 6, minus our velocity initial, which we got as 1, all divided by our time final, which is 5, minus our time initial, which is 0. So that's seconds, and that's meters per second. If we do that division, so I'm going to take 6 minus 1, gives me 5 on the top, and that's meters per second. And then on the bottom, 5 minus 0 gives us 5, and that's seconds. So our acceleration is 1 meter per second squared. So that's how we would find that out. Something that you could actually, without even calculating this, and this is going in a constant direction, is you can see on this graph that between every thing you're going up 1, 2, you're actually going up 1 and over 1 to get there. So 1 divided by 1 is 1. It looks like it is 2 squares on this graph, but if you notice, between 2 squares on here is only 1 second. So if it only went over 1 square, it would be half a second. So it is just going up by 1 and over by 1, so it's just sort of your rise over your run when you're looking at these graphs. And you might remember that from grade 10 math, doing rise over run in like linear equations. Let's try another one here. It says, what is the total acceleration of the object in graph A? So if we look at this, there's 2 points on this graph. So we're going to use those points. If you can't see these, they've got them like right there and there. And then this one has there and there. The second one's not ideal. It's best if we have them like crossing over a line, so we're not really estimating the number. So what is the acceleration of the object in graph A? Well, we can calculate that, and we will do that right now. Not with that marker. So remember our formula. I'm just going to write it at the top. VF minus VI. And that's all divided by your time final minus your time initial, if that makes sense. So it is that change in time, so we do need to do TF and TI as well. Let's plug this in. So for our velocity final, that's this one right here. The velocity is just under 200 there. Just got to figure out 1, 2, 3, 4, 5. So each of those blocks is going up by 20. So 20, 40, 60, 80. So that's 180 centimeters a second. Minus our initial velocity, which is not at 0. It is at, I would say, halfway between 20 and 40. So we're going to say 30 centimeters per second. Both of those are divided by our time, and our time final is right here, and our time finally is just before 20, and this is seconds, and these go up by 2, 4, 6, 8, 10. Yep, so by 2s. So this is going to be 18 seconds minus our initial, which is 0 seconds. So just getting those points from the graph, we can calculate the acceleration of this object. 180 minus 30 gives us 150. And 18 minus 0 is 18. If we do 150 divided by 18, we get 18.75. Just because I don't have enough room. 18.75. And that is in meters, centimeters, just kidding. Centimeters per second squared. Okay? We had centimeters per second on the top and seconds on the bottom, so that makes centimeters per second squared, and that is our answer for that question. Okay? It is already in 2 decimal places, so we are good. The final one, B, what is the acceleration of this? Using the same formula as we see at the very top of this page, I'm going to try this one. So our final velocity, is right there. It's a little bit harder to see. It's about halfway between that block. That's 10, that's 12, 14, 16, 17, I would say. So our velocity is 17 centimeters per second. Final, and then our initial velocity is 0 because it's right on the 0 line. Divided by our time, which our time at the final right here is going down to right there. So that's just past the 5. That would be 7, right? 5, 6, 7, 8, 9, 10. Just kidding, 6. So it's going up by 1s. So that would be 6 seconds minus our initial, which is about 1.5, I believe. It's about halfway between 1 and 2. So I'm going to go 1.5 seconds. And if we calculate that out, we get, hopefully, 17 minus 0 is 17. And then 6.5 minus, 6 minus 1.5 is 4.5. So we got 17 divided by 4.5. And this is centimeters per second. So 17 divided by 4.5. We get 3.77 repeating. If we use a little arrow like that, this is 3.7778. So that would be 7, 8. And that is centimeters per second squared. Okay. That is the answer for that question, that example. All right, so that's how you get the information from the graph, and then you can put it into the formula to solve for your acceleration. I'm going to stop there, and I'll finish this off after.